Welcome back, everyone. We're diving back into the world of math today.
Oh, yeah.
And I am super excited about this one.
I am too.
This is supercavitation.
Yeah.
Have you heard of this?
I have.
It's so cool.
Yeah.
So we've got some papers, some articles, and we're ready to get into it.
Sounds good.
Are you ready?
I am, yeah. It sounds like it's gonna be a fun one. Like you said, it's ripped from the headlines of
Yeah, science fiction.
Yeah, exactly.
So cool.
Yeah, it's wild.
But let's start, at the beginning.
Okay.
What is cavitation?
Well, cavitation, think of a fast-flowing river.
Okay.
You see those bubbly swirls around rocks, especially near a waterfall.
Yeah.
That's cavitation in action.
Oh, okay.
That's the formation of vapor bubbles in a liquid when the pressure drops below a certain threshold.
Oh, so those bubbles are like vaporized water.
Exactly, yeah.
Okay.
Yeah.
But why does that pressure drop?
It's all about the relationship between pressure and the liquid's vapor pressure.
Okay.
So every liquid has a specific vapor pressure at a given temperature.
Right.
And that's essentially the pressure at which it wants to turn into a gas.
Okay.
So when the pressure around the liquid drops below that vapor pressure boom, the liquid vaporizes and forms those bubbles.
So the water rushing around those rocks is getting low pressure.
Exactly, yeah.
Causing those little bubbles.
Yeah.
But I've heard those bubbles can be really destructive.
They can be.
Like they can damage ship propellers and stuff.
Yeah, that's right.
So how is supercavitation different?
So with supercavitation, we're intentionally creating a large, stable cavitation bubble that completely envelops an object.
Oh, wow.
So instead of all those small, erratic bubbles, you have one big bubble.
Oh, that's cool.
That significantly reduces drag.
So the object is moving through the water inside a bubble.
Yeah, basically.
But wouldn't that be, really hard to steer?
Absolutely. That's one of the biggest challenges with this technology.
Yeah.
But before we get into the complexities of control, let's first understand how these objects are designed to create and maintain that bubble.
So the shape's important.
Oh, absolutely. The shape is key.
Okay.
Think sharp edges.
Yeah.
The noses of these supercavitating objects often look like flat discs or cones.
Oh, interesting.
Yeah, and this shape is specifically engineered to help form that big bubble.
So like torpedoes with pointy noses?
Yes, exactly. Like the Russian VA-111 Shitval torpedo.
Okay.
It uses rocket propulsion to achieve those initial speeds needed for supercavitation.
To get the bubble going.
Yeah, and then that specially designed nose helps maintain it.
Wow. And how fast are we talking?
Oh, these torpedoes can reach some incredible speeds, far exceeding traditional torpedoes.
Wow.
The Shval, for instance, is reported to reach speeds of over 200 miles per hour.
That's insane.
Yes, several times faster than conventional torpedoes. And it's this speed, coupled with the reduced drag from that bubble, that makes them so effective.
Okay, that is so cool.
Yeah.
I mean, it does sound like science fiction.
It really does.
But how does the math come into play?
Yeah, the math is crucial here.
Okay.
And that brings us to a key mathematical concept, the cavitation number.
Okay, what is that?
This number helps us predict whether cavitation will occur.
Okay.
By taking into account factors like pressure, fluid velocity, and the vapor pressure of the liquid.
So it's like a way to quantify the conditions.
Exactly, yeah.
That lead to cavitation.
Right.
And I imagine it's crucial for designing these supercavitating objects.
Oh, absolutely. Understanding and controlling that cavitation number is essential for designing everything.
Okay.
From the shape of that nose cone to the speed the object needs to travel to achieve supercavitation.
Wow, so the math is at the heart of this.
Oh, yeah.
But we also have some research papers.
Yes.
That delves into even more complex mathematical modeling.
We do.
Of supercavitation.
What kind of math?
What are we talking about?
We're stepping into the realm of advanced fluid dynamics.
Oh, wow.
Which involves a lot of calculus and differential equations.
Cool.
One of the key concepts used in these papers is the idea of flow planes.
Flow planes?
Yeah, so imagine slicing through the water flow around a supercavitating object, creating essentially a two-dimensional cross-section.
Okay.
That's essentially what a flow plane is.
Okay.
It allows us to analyze the complex three-dimensional flow in a more manageable way.
I see. So by looking at those flow planes, researchers can calculate the forces acting on the object.
Precisely.
As it moves through the water.
Right. These calculations are crucial for understanding things like the object's trajectory, its stability, how it interacts with that cavitation bubble.
Wow, so much math.
There is.
Just to understand the basics?
Yeah, and it gets even more complex when you start talking about controlling and maneuvering these objects within their bubbles.
Ooh, okay.
But that's a topic for our next segment.
All right, I am very excited to get into that next time.
Yeah, it's going to be good.
But for now, we'll take a quick break and come back to explore those fascinating applications of this technology.
Sounds good.
All right, so we've covered some of the math behind these supercatacating objects.
Yeah, it was barely scratched the surface.
But I want to talk about the,
of course,
applications of this. Yeah. We've mentioned torpedoes.
Yeah.
But where else are we seeing this?
Well, as you might imagine, the military applications are pretty significant, given the potential for speed and stealth.
Right.
Besides torpedoes, there's been a lot of interest in developing supercavitating projectiles.
Oh, interesting.
Essentially bullets that can travel underwater at incredible speeds.
Underwater bullets?
Yeah.
How do those even work?
That's where that supercavitation magic comes in again.
Yeah.
These projectiles are designed with a sharp nose, similar to the torpedoes we discussed.
Okay.
And that helps create the cavitation level around the bullet as it's fired.
Right, so it's not really traveling through water?
No, it's mostly moving through vapor.
Oh, okay.
Which drastically reduces the drag, allowing it to maintain that velocity over much greater distances.
Oh, that's so cool.
It is.
But I imagine accuracy must be a real challenge with those.
Absolutely. That's one of the biggest hurdles researchers are facing.
Yeah.
It's not easy to maintain stability and trajectory control within that bubble.
Right.
You can't just rely on traditional rifling techniques or aerodynamic fins.
Like a regular bullet.
Yeah, exactly.
So how do they even control these things?
Well, there are a few different approaches being explored.
Okay.
One method is using a technique called base bleed.
Okay.
Where a small amount of gas is released from the rear of the projectile.
Okay.
This gas helps to stabilize that cavitation bubble.
Oh, okay.
And can even be used to make slight adjustments to the trajectory.
So they're fine-tuning the bubble.
Exactly, yeah.
That's really cool.
It is pretty cool.
But let's step away from weaponry for a minute.
Okay.
Are there applications in other areas?
There are.
Like, what about transportation?
Right.
Have we seen that?
Yeah, there has been a lot of interest in the transportation side of things.
Okay.
One of the most ambitious projects was DARPA's Underwater Express program.
What was that?
They were aiming to develop a high-speed underwater craft.
Oh, wow.
That could transport personnel and cargo much faster than current submarines.
Okay, how fast are we talking?
The goal was to reach speeds of up to 100 knots.
Wow.
Which is roughly 115 miles per hour.
That's insane for underwater.
Yeah, it's much faster than most modern submarines.
Yeah, what were some of the challenges?
Well, as you can imagine, scaling up this supercavitation technology from small projectiles to a large vessel presents a lot of engineering hurdles.
Yeah.
One of the biggest challenges was creating a cavitation bubble that was large and stable enough to envelop the entire craft.
Okay, I can imagine the energy requirements must be enormous.
Yeah, it's a significant engineering feat.
And then the control, right?
Oh, absolutely. Control is a huge issue.
Yeah.
How do you steer and maneuver something that's essentially gliding through vapor?
Yeah, it's wild.
Right. So they were exploring different methods,
okay,
including using strategically placed hydrofoils and control surfaces to try to manipulate the shape and direction of the bubble.
Oh, interesting.
It's almost like, I guess, surfing a wave.
Yeah.
But instead of a wave, you're riding a bubble.
That's a really good analogy.
Yeah.
So what happened? Did they ever create a working prototype?
Unfortunately, the Underwater Express program was eventually shelved.
Oh.
Due to some technical challenges and funding constraints.
Right.
But the research they did during that program really contributed a lot to our understanding of supercavitation and its potential for these large-scale applications.
Right, so those high-speed dreams may still be a ways off.
Yeah, they might be.
But are there any other, maybe more practical applications?
There are.
That are being explored?
Yeah, and some of them might surprise you.
Okay.
Researchers are looking into using supercavitation in the field of medical devices.
Medical devices?
Yeah.
How?
Well, one promising area is focused on using microbubbles and ultrasound to create these tiny, highly localized supercavitation effects inside the body.
Tiny bubbles inside the body.
Yeah, it sounds a little counterintuitive, but it has the potential to be incredibly beneficial.
Okay, how?
One application is targeted drug delivery.
Oh, okay.
So by creating those microbubbles near specific cells or tissues, doctors could deliver medications with much greater precision.
Wow, and fewer side effects.
Yeah, exactly.
So it's like a tiny supercavitating torpedo.
Yeah, in a way.
Carry medicine.
Yeah, that's a good way to put it.
That's so cool.
It is pretty cool.
Are there any other medical applications?
Yeah, there are. They're also exploring its use in non-invasive surgery.
Oh, wow.
So the idea is to use focused ultrasound
Okay.
to create those microbubbles near tumors or other unwanted tissues.
Right.
And then use the energy from those collapsing bubbles to basically break up the targeted area without needing traditional incisions.
Surgery with bubbles? That's amazing.
It is pretty amazing.
It seems like we've only scratched the surface of what supercavitation can do.
I think we have.
But before we move on, I wanted to ask about something you mentioned before.
Okay.
The environmental impact
Right.
of all these bubbles.
Right, of course.
Could there be any negative consequences?
That's a really important question.
Yeah.
And one that researchers are definitely taking seriously. As we discussed, the collapse of those cavitation bubbles can generate a lot of heat and pressure.
Right.
And while we can harness that for good...
Right, like in the medical application?
Exactly.
Yeah.
It could also have some unintended consequences for marine life.
Yeah, I could see that.
Especially if these technologies are used extensively.
So we need to proceed with caution.
Yeah, we need to balance those potential benefits
with
a responsible approach to its development and deployment.
Of course, conduct thorough research and impact assessments.
Absolutely.
Okay, it seems like there's still a lot to learn.
There is.
About supercavitation and its long-term effects.
Yeah, for sure.
But from what we've explored today,
it's
clearly a very fascinating and versatile technology.
It is.
With the potential to really revolutionize a lot of different fields.
Oh, absolutely.
From underwater warfare to medicine and maybe even transportation one day.
Yeah, it's really remarkable how far it's come.
Yeah, speaking of advancements, are there any new developments in this research that you're excited about?
Yeah, one area that I'm really interested in is the development of new materials and coatings that can enhance those supercavitation effects.
Interesting.
So these materials are designed to reduce friction even further and improve the stability of that cavitation bubble.
Oh, cool.
Which could lead to even faster and more efficient supercavitating objects.
So we're talking about materials that are almost frictionless underwater.
In a sense, yeah, it's still early days, but it's a really exciting area of research.
Yeah, it has the potential to push those boundaries even further.
Oh, for sure.
This has been a really eye-opening look at supercavitation.
It has.
From the math to those mind-boggling applications.
That's really cool.
It's amazing to see how science and engineering are coming together to kind of, unlock the potential of this phenomenon.
Yeah, and it highlights a really important point that often the most groundbreaking discoveries come from looking at seemingly mundane things like bubbles, like finding the extraordinary hidden within them.
I like that.
Yeah.
Well said.
Thanks.
So I want to thank everyone for joining us for this deep dive into the world of supercavitation.
Yes, thank you.
We hope you've enjoyed it.
We hope you learned something.
Yeah.
And maybe even had your mind blown a little bit.
Yeah, until next time. Keep exploring, keep questioning.
Absolutely.
And keep diving deep.
Keep diving deep into the wonders of math and the world around us.
Great. It really is amazing to think about.
It is.
How something is,
simple.
Yeah, as simple as a bubble can have such a huge impact on how we move through water.
It's incredible.
We talked about, torpedoes and bullets.
Yeah.
Even like high-speed transportation and medical applications. It
really opens up a whole new...
Yeah, a whole new world of possibilities.
Yeah, absolutely.
And it sounds like there are still...
Oh, yeah.
A lot.
Trial says definitely, but
the progress,
especially in material science and control systems, has been really promising.
Yeah, it's really cool to see where things are headed.
Yeah, it makes you wonder what the future holds.
Exactly. What else can we achieve with this, crazy phenomenon?
Right.
Imagine, underwater travel being as fast as air travel. That would be
wild.
So cool.
Yeah, although... Like with any powerful technology, we have to be careful,
of course,
about the implications and make sure we develop it responsibly.
Right, and we talked about the environmental considerations.
Yeah.
But there are also ethical aspects to think about.
Oh, absolutely.
Especially as it gets,
more powerful.
More advanced.
Yeah, as it becomes more sophisticated.
Right.
We need to think about how it could be misused.
Yeah, especially in things like military applications.
Right.
So
it's a good reminder that we need to be having these conversations.
Yes, definitely.
Along with the scientific advancements.
For sure. Well, this has been an incredible journey into the world of supercavitation.
Yeah, we've learned a lot.
We started with the basic physics.
Yeah.
Then we got into some of that complex math. And then all of those mind-blowing applications.
Yeah, it's pretty amazing.
It really is a testament to, human ingenuity.
Yeah.
And just the power of scientific exploration.
It really is.
It makes you wonder, what else is out there?
What else is out there?
That we haven't even thought of yet.
Yeah, right. Exactly.
So I want to thank all of our listeners.
Yeah, thanks for joining.
For coming along on this mathematical adventure.
It's been a pleasure.
We hope you found it insightful.
Engaging.
And maybe even a little bit mind-blowing.
A little bit mind-blowing, yeah.
And until next time, keep exploring.
Absolutely.
Keep questioning.
Keep questioning.
And keep diving deep.
Keep diving deep into the wonders of math.
Yes.
And the world around us.
I love it. Well, that is it for today.
It is.
We'll see you next time.
See you later. Play today.